for the introduction, and also I'd like to thank the organizers for the invitation. So actually this topic is what I had been working on 8 years ago, but at that time I had some difficulty that I didn't make it, but recently some people resolved the problem, so I can write down this paper. So yeah, I'm gonna tell you some, I'm gonna introduce some problems, classification problems in equivariant symplectic geometry. So let me begin with some basic terminology. So I think almost all of you already familiar with this notion. Fano variety is a complete smooth variety whose anti-canonical boundary is ample. So there are some equivalency definitions. For instance, projective variety is Fano if and only if there exists a Kähler form which represents the first class, or also equivalently, the pairing with the first class with any algebraic curve is positive. So a baby example is of course Pn, and any smooth hypersurface of degree less than or equal to n, or the complete intersection of smooth hypersurfaces whose the sum of all degree is less than or equal to n, or generalized Frege variety, and so on. And the famous theorem by Kolla, Miyaoka, and Mori, and they prove that for each dimension, there are only finitely many deformation types of smooth Fano variety. So in algebraic geometry, people are trying to classify those objects in each dimension. So for instance, we will see the classification in here.
What do you mean by generalized? That it means all partial flags or all different Lie types, or what?
Yeah, all different Lie types. Okay. Yeah, G-mod parabolic subgroup.
And also any partial flags?
Yeah, sure, yeah.
What do you mean by deformation type?
Deformation type is, so if two varieties deformation equivalent, that means there is some certain one dimension or more family of the variety over certain affine space and with certain conditions. So in general, we use the flat family of variety. So if two variety appears, then they are called the deformation equivalent.
So they are not necessarily isomorphic?
Not necessarily isomorphic. Yeah, their complex structure may be different. Yeah, but they are diffeomorphic. Yeah. Okay. So now there is a symplectic analog of Fano variety, which we call the monotone symplectic manifold. So you know what a symplectic form is, and it is called the monotone if the cohomology class of symplectic form is positively proportional to the first class of Tm. So actually this is, you can think of this notion is a certain generalization of smooth Fano variety. So,
didn't you insist that the first Chern class be equal to omega in the previous?
Sorry?
In the previous slide.
Okay, oh, yeah.
It's just first Chern class has to be the form, right?
Sure, yeah.
But if you mean every lambda is one?
Yeah, if we have any symplectic form or Kähler form, we may always scaling. We can scale.
You can scale.
Yeah. So we always make lambda to be 1. So, yeah. So the following question is classical one in symplectic geometry. So the question is whether every closed monotone symplectic, to actually find monotone non-Kähler symplectic manifold. That's the main problem. So in lower dimensional case, it is positive. So for instance, if dimension is 2, then actually there's only one type of such a manifold, P1, And when dimension is 4, then there are 10 diffeomorphism types. So P2, P1 cross P1, and blow up of a P2 at K generic points, where K is less than or equal to 8. So they are, in algebraic geometry, they are called Delpech surfaces. And actually, in recently, maybe 5 years ago, the Finney and Panop proved that there exists non-Kähler closed monotone symplectic manifold in dimension 12.
Non-Taras Panop?
No, actually it is.
What's special about 12? What's special about 12?
Actually, I don't know exactly. Yeah, I'm sorry. Actually, and Panop is Dmitry Panop. Yeah, and the question is still open in 6, 8, and 10. Okay, so in dimension 6, some people are trying to find such kind of example or prove the conjecture. So there are some positive results. So first theorem is due to Su-Tolman and Dusa-Mektop, and they have shown that if when M is 6-dimensional monotone symplectic manifold, and if M has a Hamiltonian circle action, and in particular when the second Betti number is 1, then actually M is Fano, and there are exactly 4 types of such manifold, up to S1 equivalent symplectomorphism. So, and also, and recently, Lindsay and Panop proved that whenever M is a 6-dimensional monotone symplectic manifold with a Hamiltonian circle action, then it is simply connected. So here, it is well known that every smooth Fano variety is simply connected. So actually, they serve a certain evidence to make the conjecture is true, possibly true. And today I'm going to talk about the following theorem. So if we have a 60-dimensional monotone symplectic manifold, and especially the Hamiltonian action is semifree, and furthermore, if we assume that minimal or maximal fixed component is of dimension less than or equal to 2, then M is Fano.
Are there any examples?
These examples?
Are there any examples where the fixed component is of dimension less than or equal to 2?
Yeah, sure. For instance, in CP3 case, we have a semifree circle action whose fixed component is sphere and sphere. And actually so for instance, the P1 times P1 times P1, we have 8 isolated fixed points. So that also, the theorem is available. So I want to explain the theorem and sketch the proof. Okay. So first, I want to say some basic stuff. So as you know, the symplectic action means the action preserving the symplectic structure, and Hamiltonian circle action means if there exists a moment map such that Ix omega equals to minus dh. Here the minus is just a sign convention, so you may ignore the sign if you want. And the semi-free action means the action is free outside the fixed point set. So the orbit type is, there are exactly 2 orbit types, fixed point and free orbit. And the main technique is to analyze the properties of moment map. So if we have a Hamiltonian circle action, then the moment map is a perfect Merz-Bab function. And in particular, every index is even. And the fixed points that coincide with the critical point set of the moment map. And the Merz-Bab index is actually can be computed as twice the number of negative weights. you know what the weight means here. And of course, the moment map is S1 invariant. So every level set is itself a S1 manifold. And whenever R is a regular value, we make quotient by S1 action so that we get some nice space, which I call the reduced space at level R. So here, if R is a regular, then MR is in general obifold with cyclic quotient singularity. And if you assume that semi-free, then every orbit is free so that the quotient is smooth. And the last one is important in this talk. So if dimension is 6, then even though C is a singular, the quotient is smooth. So this is the particular feature in the semi-free action on 6-dimensional manifold. And more generally, we can generalize this. There's some slightly generalization of this statement, but in this talk we only need this enough. This is enough. Okay. And now I explain what monotonicity implies. So if we assume that omega equals to C1 at the first class of M, so here I take lambda to be 1, then we can say that we can adjust the moment map by adding certain constant so that the following equality hold. Here the H is the moment map, and the right-hand side, the sigma of Z is the sum of weights. So for instance, let me give an example. If dimension is 6, and if the action is semi-free, and suppose that the maximum is isolated point, fixed point, then at the maximum, the weight is -1, -1, -1. So the sum of the sigma Z max is -3. So actually, by this equality, H Z max should be 3. And this equals to 3 minus dimension of Z max. So, I mean, anyway, the first statement says that if we assume that monotonicity, then we can read off the moment map value in terms of the weight of the fixed point, and vice versa. And the second one is, and also, such kind of moment map is called a balanced. And the second statement is, if moment map is balanced, then if we take reduced space at level 0, then, and also, oh, I forgot to say that what omega R is. Sorry. Yeah, actually, the quotient space always admits the induced symplectic structure. So I denote by omega R. Okay.
I mean, when you say semi-free, but that the fixed point set is not necessarily isolated.
Oh, sorry?
When you say the action is semi-free,
yes,
but the fixed point set is not necessarily isolated.
No.
And then why in this next page?
Yeah. So, sorry.
If dimension M is 6, the action is semi-free, then
okay. So
assuming that this is fixed point. I mean,
yeah. So no. For instance, if Z max is a sphere, for instance, then you know the
you have to decrease by dimension.
Yeah, decrease by dimension. Yeah, because twice the dimension means that the zero waste space.
Dimension, complex dimension.
Yes. Yeah. Sure. Yeah. Definitely. Yeah. And if H is a balanced moment map that we choose in the first statement, then the reduced space with the induced symplectic form at level 0 is again monotone. So if we assume that dimension M is 6 and the action is semi-free, then even though 0 is a singular value, critical value, we get a four-dimensional monotone symplectic manifold. So this guarantees that by the classification of four-dimensional monotone symplectic manifold, we see that M0 is one of 10 types that I explained before. So we know that the candidates of M0. Okay. So now I want to explain the main idea, how to classify those kind of space. So first we assume that Hamiltonian S1 manifold with a moment map H. Then because we assume that M is compact, we have a finite number of critical values. So from C1 to Ck in increasing order. Then we decompose M into several manifolds with boundaries. So here, the first, on the left-hand side, this is a manifold with two boundaries, manifold with one or two boundaries, having exactly one critical value, Cj. And the right-hand side is the manifold with two boundaries and have no critical values. So, just to cut the manifolds along the, yeah. So we call these pieces slices. So more specifically, I will define the two kinds of slices. Regular slice is just a free Hamiltonian S1 manifold with boundary, with two boundary, like this. It's just a definition. And critical slice is semifree Hamiltonian S1 manifold with a boundary and has a unique critical value. So more specifically, if there is if the critical value is in the interior of this interval, then we call the interior slice. And if the critical value is the maximum, then we call maximum slice. And if C is a minima, then we call minimal slice, and so on. And also we define the isomorphism of slices by this diagram, this commuting diagram. So actually, two slices are isomorphic to each other whenever there is an S1 equivalent symplectomorphism, like this. And so the strategy goes as follows. So if we have some close to Hamiltonian S1 manifold, we divide our manifold into several slices, and we investigate each slices, and we reconstruct our manifold using these slices. So the resulting manifold is the same as the old one. So, okay. So first, I want to explain how critical slices is determined. So first, suppose that we have a certain critical slice and sigma k, the image of moment map here, and suppose that we have a certain critical value here. And further, we assume that the action is semifree and the fixed point set is of index 2 or coindex 2 respectively. Then the Guillemin and Sternberg proved that the reduced space at level B is the blow-up of MA along this fixed point set. And moreover, if two critical slices satisfy those three properties that I will explain in a minute, then the slices are actually equivalent for reducing this interval appropriately. So the three condition is, first one is, if two critical slices, we have two critical slices, and then the first condition is the reduced space at the minimum is diffeomorphic, and also, at the level A1, the action is free action, S1 free S1 action. So we have a principal bundle. I mean K1 inverse A1 and the projection to the N1A1. I'm sorry for the complicated notation. But anyway, here the E means the Euler class of S1 bundle. So, okay. So here we have two critical slices, and there are certain C1 or C2 here. And then here the level K1 inverse A1. Here the level K2 inverse A2. And at this level, these are manifold, S1 manifold, free S1 manifold. So it has a quotient map to, N1, A1, quotient by S1 action. And this is a principal S1 bundle, and E means the Euler class of the S1 bundle. And the third one is, there is a symplectomorphism between the critical level, the reduced space at C1, and the reduced symplectic form at C1. And here are those on N2 part. And moreover, this symplectomorphism should send this fixed point set to those fixed point set. So anyway, to summing up, the Guillemin and Sternberg says that if we have two critical slices, then if we want to check whether two critical slices are diffeomorphic to each other, then we just look up the diffeomorphism type of reduced space, and then compare their Euler class of the principal S1 bundles, and finally we should look at whether two reduced space are symplectomorphic to each other at the critical level, and especially whether there is a symplectomorphism sending this component to this component. So if we want to, if we check the three properties and they are done successively, then we can say that two critical slices are diffeomorphic to each other. So anyway, we will see the examples later. And for the regular slice, it is much more easy. So here's the fact. If we have two regular slices, so as I said before, the regular slice means the free S1 manifold with two boundaries. So if we want to check whether two regular slices are isomorphic to each other, then we just compare their reduced symplectic form and the Euler class. But actually, the first one is implied by the second one. So we only need to check the second one for each t. But the problem is it very difficult to check whether two symplectic forms are equivalent or not, because we should find certain symplectomorphism. So our hope is like something like this. So the comparing the cohomology classes are much more easy. So our hope is if two cohomology classes are equal for each t, then we hope that it implies the second one. And actually, in our case, this is true. We'll see later. Okay, and so also to explain our theorem, we need the following notion: symplectic rigidity. Before to explain this, I first state the Gonzalez theorem. So here's the thing. if every reduced space is symplectically rigid, that I will explain later in a minute, then the following, then this star condition hold. So that means if the reduced space is symplectically rigid, then we only need to compare their cohomology class, not real symplectic forms. And moreover, if we have a family of slices which are compatible in some sense, here the compatible means that the slices can be glued together so that they produce some closed manifold, then the way of gluing these slices is unique. So the classification of classification problem reduces the classification of slices compatible with each other. So here the symplectically rigid is defined to be defined by those three properties, but actually I just briefly mentioned the three things. One is the symplectic form is unique for each cohomology class. That means if we have two symplectic form on the same space, and then if they have the same cohomology class, then they should be diffeomorphic. I mean, there is a diffeomorphism which sends the one to another. And the second one is deformation implies isotopy, which means that if we have a family of symplectic forms that connects certain two symplectic form omega 0 to omega 1, and if they have the same cohomology class, then these paths can be homotope to an isotopy. That means there is an homotopy which sends this path to those paths. And the second one is certain technical assumption, but anyway, we used this theorem. So it is, and the following theorem is some simple examples of a symplectically rigid space. So P2, P1 cross P1, and P2, the blow up of P2 at most K times blow up, for a K is less than or equal to 3. Okay. So you just memorize those 5 spaces are symplectically rigid, and whenever the reduced is symplectically rigid, then we only need to compute their cohomology class to classify the slices.
So those 5 spaces are the only known symplectically rigid spaces, or do you have some sufficient properties about the space which are symplectically?
Actually, as far as I know, when case 5, it is not rigid. It is proved by Paul Seidel, and in 4 case, I think it is not known.
But they are all 4-dimensional. Right?
Yeah. Here the K is the number of points, blowing up point.
All these examples are 4-dimensional.
Yeah.
Any higher dimensional. Some general property. It's the sufficient condition some of the characteristics describes rigidity, or.
Yeah, I don't know. I think it is the.
So that's a very difficult to be satisfied.
Yeah. And the proof of this theorem requires the deep understanding of pseudo-holomorphic curves technique. Yeah. So summing up, our story goes as follows. If we have two 6-dimensional closed semifree Hamiltonian S manifold, M1 and M2, and we assume that this condition. So if we can check every reduced space is symplectically rigid, and the fixed point data coincide, then we deduce that two manifolds are S1 equivalently symplectomorphic. So this is not obvious, but anyway, we can prove this statement. So our strategy is classify all fixed point data. I also defined what a fixed point data is, and prove symplectic rigidity of the reduced space for each case. And for each fixed point data, we will find the corresponding Fano variety with a semifree cis direction. Then, by the previous statement, we can show that every our manifold is Fano. So here are the definition of fixed point data. So I mainly concentrate on the 6-dimensional case. So suppose we have a semi-free closed monotone manifold. And then the fixed point data consists of the followings. Here are the MC for each critical value. MC omega C is the reduced symplectic manifold at level C. So even though C is a singular, the critical value, this space is a smooth manifold. And from ZC1 to ZCKC, these are fixed components lying on the level set C, at level C. And we can see that using this embedding, we can see that each ZCI is a symplectic submanifold of the reduced space. And here the EPC plus minus is denoted by the Euler class of the principal epsilon bundle over some regular value near C. Okay. So this information, the family of this information is called the fixed point data. But all right. And Gonzalez shows that if M is our manifold and every reduced space is symplectically rigid, then M is determined by fixed point data up to S1 equivalent symplectomorphism. So the classification problem of our manifold is the classification problem of the fixed point data under the assumption that every reduced space is rigid. But the problem is it is very difficult to classify the fixed point data because, but in here this data includes this embedding information. So even though our fixed component is the diffeomorphic, but the embedding is different, then the fixed point data should be different. So actually it is almost hopeless to classify our embeddings of a given manifold. But of course, the computing its homology class is much more easy problem. So our hope is the following. So actually, homology class, we hope the homology class determines the embeddings. It is in general, may never be true in general, but this holds in our space case. So actually, that was the difficulty in 80 years ago, but recently this is solved. So instead of fixed point data, I will define topological fixed point data, which is the homology or cohomology version of the topological the fixed point data. So here, instead of a symplectic form, we take the class of symplectic form, and here, instead of embedding of fixed component, we record its homology classes, and the Euler class is remained. Then it is much more easier to compute the topological fixed point data rather than the fixed point data. Okay, so here's the sketch of the proof. The first step is classify all possible topological fixed point data that our manifold can have. And we show that in our case, the classification of a topological fixed point data, we can show that every reduced space is one of these five types. And actually they are known to be symplectically rigid. And the second step is topological fixed point data determines fixed point data uniquely. So that means if we have two manifolds having same topological fixed point data, then they should have they have same fixed point data. And this can be done by these two procedures, but I skip it because I want to show some example. And the step 3 is find, for each topological fixed point data in our classification, we want to find some Fanos threefold with the Hamiltonian S direction having the same topological fixed point data, but we can make it this step by aid of Mori and Mukai's classification of smooth Fanos threefold. Okay, so these are 18 types of possible topological fixed point data for our manifold. And here, we can record something like this. Oh, I'm sorry, this is too small. This is a z minus 3. So here, this line is minimal fixed point set. And this one is fixed point set at level -1. This one is fixed point set at level 0. And level 1, level 2, level 3, and so on. This one is just computing first number by using localization. So we can read it like this. In the first line, 1, 1, 1, the minimum is isolated point, and in the middle, there is a certain fixed two sphere, and this sphere, the Poincare dual of this sphere, this sphere is of degree 2 inside of CP2, which is the level set, which is the reduced space at level 0, and the maximum is point. So the corresponding picture is this. So if we have a coadjoint orbit, regular coadjoint orbit of SO5, then there is some maximal torus T2 action. Then their moment map image is the rectangle, and their GKM graph looks like this. And we choose a certain circle actions on the y direction. Then you see that we have a minimal fixed point and fixed sphere and maximum fixed point. And this corresponds to the first line. And for the second line, here the minimal fixed point is point, and on the -1 level, 3 fixed point, and 1 level, 3 fixed point, and maximum is P1. So you see that it is a very famous example, which is P1 cross P1 cross P1. So to see this, this is a toric picture, and we choose some direction such that there's some isolated minimum and 3 isolated fixed point at -1 and 3 fixed point at 1 and isolated maximum, something like this. And finally, I will show you one more example. The third one is minimum is point and -1. There's 1 fixed point at 0. There are 2 disjoint spheres, and at level 1 there's 1 other point and maximum isolated maximum. And this corresponds to this. Actually, this can be constructed by trivial P2 bundle, by projectifying the direct sum of a trivial P2 bundle, trivial bundle over P2 and a line bundle of degree 2. Then this is a toric variety corresponding, the corresponding Desargues polytopic looks like this. And there is a certain T2 action, the projection, then we get this GKM graph. And if we take the y direction, then we see that there's an isolated minimum and isolated fixed point at -1 and 2 copies of fixed sphere and 1 fixed point and 1 maximum. So this picture corresponds to, and you also check that the action is semifree by pairing these vectors and the direction we have chosen. And the method for describing the classifying these topological fixed point data, actually, it is not quite difficult. We use 3 things. One is adjunction formula for symplectic form manifold. and certain localization techniques and Huysman-Techman theorem, but it is too much technical, so I will just briefly mention one final things. So we classify all topological fixed point data, and we find the corresponding Fano variety. Then the reason why we can conclude our manifold is Fano. The reason is like this. So first we find the Fano variety, and the second one and third one is the symplectic rigidity implies that the regular slices and grading, the slices are uniquely determined, and grading data is also uniquely determined. And we use certain theory of a four manifold, and actually, they should be coincide. There must be only one candidate for each topological fixed point data. So that's the outline of the proof, and so I stop here.